Welcome to section 8.2, solving quadratic equations by the quadratic formula. Our goals in this section are to solve quadratic equations using the quadratic formula. We're also going to use the discriminant of the quadratic formula to determine the type and number of solutions. You may have seen the quadratic formula before. Essentially, the quadratic formula is a formula that gives you the solutions to a quadratic equation. So, if I have a quadratic equation, ax squared plus bx plus c equals 0, then x, the solutions to that equation, will be negative b plus or minus the square root of b squared minus 4ac all over 2a. You take the coefficients from your quadratic equation, plug them into the quadratic formula, and then simplify. The one really important thing to remember is to be sure that your equation is in standard form before you decide what a, b, and c are. So up here, you really need to have it say ax squared plus bx plus c equals 0 before you figure out what a, b, and c are to plug into the formula. Also, just as a point of interest, I'd like you to know that this formula comes from completing the square. So if you take your ax squared plus bx plus c equals 0, and you go through that whole process of solving by completing the square, remember from section 8.1, then you'll end up with your answer being x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. The point is, you don't have to just believe that the quadratic formula works. It actually comes from something that you know how to do. It's not magic. So let's do a couple examples of solving these quadratic equations using the quadratic formula. My first example is 2x squared minus 6x minus 1. I'm going to start by jotting down what my formula is. The quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. By the way, if you're having trouble remembering the quadratic formula, look it up on YouTube. There are some funny videos of kids singing about the quadratic formula. Now that I've got my quadratic formula written down here so that I can use it easily, my next step is to figure out what a, b, and c are. My quadratic equation is already in standard form. So a is the coefficient of x squared, which is 2. B is the coefficient of x, which is negative 6. And c is the constant, which in this case is negative 1. Now I just need to plug all this stuff into my quadratic equation. So x equals negative b, which is negative 6, plus or minus the square root of b squared, again, b is negative 6, minus 4 times a times c. A was 2, c is negative 1. I'm going to extend my square root all the way across here. And this is all divided by 2 times a, which is 2. I'd like to point out this habit that I have of replacing the variables with parentheses before I plug in the numbers. This helps me keep from mixing up my negative signs. So now as I continue to work on simplifying this, I should be able to keep track of my negative signs, I hope. I've got the opposite of negative 6, which is regular 6, plus or minus the square root of negative 6 squared. Now remember, when it's in parentheses like this, it means negative 6 multiplied by itself, which is positive 36. And then minus 4 times 2 times negative 1. Let's see, 4 times 2 is 8, and 8 times negative 1 is negative 8. But I'm subtracting it, so this is going to end up being a plus 8. And then this is all over 4. Now I'm just going to continue simplifying. This is 6 plus or minus the square root of 44 all over 4. At this point, I'm really pretty happy that we've gotten here. However, this square root can be simplified a little bit more, so we're going to go ahead and do that. Notice that the square root of 44 is the same as the square root of 4 times 11. So the square root of 4 is 2, so this can become 6 plus or minus 2 square root of 11 all over 4. The last thing I'm going to do to finish simplifying this is notice that all of my terms have a 2 in them. So I can cancel a 2, making this 3 plus or minus the square root of 11 over 2. I want to be very clear that both this answer and this answer are the same. They are the same numbers. It's just that this one is more simplified. Typically on a test, you'll see that we might take off 1 point or maybe 2 points if you don't simplify. But if you're checking your homework in the back of the book and you have this answer, and you see that the book has this answer, don't panic. Don't crumple up your work and throw it away. Chances are you just didn't simplify the way that they did. And finally, before we move on to the next example, I want to say that you should probably leave your answer in its exact form like this, unless it's a particular application and you want to get a decimal approximation. Usually, though, we're going to ask you to leave your answer in its exact form, which means that it'll look something like this when you're done. Okay, let's move on to the second example. Here I have 3y squared equals negative 6y minus 5. Before I can start doing anything with this, I need to get it into standard form. That means that I need to add the 6y and the 5 to the other side of the equation, which gives me 3y squared plus 6y plus 5 equals 0. Now, if you're thinking, why couldn't I just subtract the 3y squared to the other side? You're not wrong. You will get the same answer whether you move the 6y and the 5 over or whether you move the 3y squared over. As long as you keep your signs straight, you'll get the same answers. I tend to move things over so that I have as many positive numbers as possible because I figure I'm less likely to mess up my negative signs. Now that I have this guy in standard form, I can pick out what a, b, and c are. A is the coefficient on the squared thing, so a is 3. B is the coefficient on the single thing that's not being squared, so b is 6. And 5 is my c, since c is the constant. Next up, we'll plug everything into that quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now I just need to work on simplifying this as much as I can. I'll have x equals negative 6 plus or minus the square root of 36. It's like this is going to be minus, let's see, that'll be 60 all over 6. Now, 36 minus 60 under my square root is going to get me a negative number. So I'm going to have some imaginary answers here. I have negative 6 plus or minus the square root of negative 24 over 6. Now, again, I'm just working on simplifying my answer here. This is negative 6 plus or minus the square root of 24 with an I outside. Remember, a negative under the square root is the same as an I outside the square root. Now I can continue to simplify the square root of 24. Since 4 will go into 24, I can make this negative 6 plus or minus the square root of 4 times 6. Got my I still on the outside there. There's a 6 on the bottom. The square root of 4 is 2, so this is negative 6 plus or minus 2 square root of 6, and I all over 6. Now I notice again I have a 6, a 2, and a 6. I can cancel a 2 from all of those, which gives me, at last, negative 3 plus or minus the square root of 6, the i's on the outside, all over 3. Phew, this problem might have seemed kind of long, but I want to remind you, you really did the bulk of the work back here, where we plugged the right numbers into the right spots in the quadratic formula. After that, we were simplifying, which took a little bit of time to be sure, but really isn't anything new. And now, of course, it's time for you to try solving one. Here you've got x squared minus 13 equals 5x. So you're going to want to get that into standard form before you try solving it. Go ahead and pause the video, give it a try, and we'll look at it together when we come back. And we're back. So the first thing that I did when I started trying to solve this using the quadratic formula was to write down the quadratic formula so that I would know what I was working with. The next thing to do is get this into standard form. So I need to subtract the 5x from both sides to get it set equal to 0. That left me with x squared minus 13 minus 5x. I decided to rearrange the negative 13 and the negative 5x so that I have x squared minus 5x minus 13 equals 0, putting these in order from biggest degree to lowest. That way I won't accidentally think that the 13 is my b when it's really not. Now I can read off what a, b, and c are. A is 1 since the coefficient of x squared is 1. B is negative 5 since the coefficient of x is negative 5. And c is 13 because the constant is 13. Then I plug all those guys into my quadratic formula and start simplifying. I end up with 5 plus or minus the square root of 77 over 2. Now, the square root of 77 doesn't simplify any further. I hope you didn't spend too much time trying to simplify that one, because this is as simplified as it gets. We can leave our answer just like that. Now we're going to take a look at the discriminant. The discriminant of the quadratic formula is the stuff under the square root. So it's b squared minus 4ac. The discriminant can tell us how many and what type of solutions to expect. It's called the discriminant because it lets us discriminate between different types of quadratic equations. Now we're going to play a little bit of a thought game to see what the discriminant can tell us. Let's say that the discriminant is positive. That means that I get something like -5 plus or minus the square root of, let's say, 36 all over 2. When I go to simplify this, I'm going to have -5 plus the square root of 36, which is 6, all over 2, and -5 minus the square root of 36, which is 6, all over 2. This gives me two distinct answers. If the discriminant is positive, you get two real answers. Now let's take that same situation and say that the discriminant this time is 0, so the stuff under the square root is 0. Then I would have something like -5 plus or minus the square root of 0 over 2. But the square root of 0 is 0. So when I break this out, I get -5 plus 0 over 2, and I get -5 minus 0 over 2. These two numbers are really the same. This is going to be -5 halves, and this is also going to be -5 halves. So even though I split it up into a plus or a minus, adding 0 and subtracting 0 are really the same thing. Doesn't make any difference to my final answer. So if the discriminant is 0, I really only get one answer, but it's a real number, so one real answer. Finally, let's look at what happens if the discriminant is negative. Let's say that I have -5 plus or minus the square root of -36, still all over 2, say. This gives me an imaginary number, right? This is the same as -5 plus or minus 6i, since the square root of a negative gives me an I, and the square root of 36 is the number 6. And it's all being divided by 2. So this gives me two answers, -5 plus 6i over 2, and -5 minus 6i over 2. So this gave me two possible answers, but they're both imaginary. So if the discriminant is negative, we have two non-real answers. In summary, if the discriminant is positive, we'll have two real answers. If it's 0, we have one real answer. And if the discriminant is negative, we have two non-real answers. A lot of students like to compute the discriminant separately when they're solving an equation using the quadratic formula. So off to the side, they'll figure out what the discriminant is, say 36, and then they just need to plug in -b plus or minus the square root of the discriminant all over 2a, which can make the whole process of solving using the quadratic formula a little bit cleaner, maybe a little bit shorter. Let's do an example of using the discriminant to figure out how many solutions and what type of solutions this particular equation will have. I have 3x squared equals 5 minus 7x. Now again, first things first, I need to get this into standard form. So I'm going to add the 7x to both sides, and I'm also going to subtract 5 from both sides, which ultimately gives me 3x squared plus 7x minus 5 equals 0. Now I'm ready to compute the discriminant. Notice that a is 3, b is 7, and c is -5. The discriminant is b squared minus 4ac. So I just plug my numbers in here. I'll have 7 squared minus 4 times 3 times -5. And when I simplify that, I get the number 109. Because the discriminant is positive, I know that I will have two real solutions, which is what this problem was asking for. Now, this problem was only asking us to figure out how many solutions and what type, which we did. We found that there are two solutions and they're real. But as a quick little bonus, I want to show you what it would look like if we continued to solve this now that we know the discriminant. If we solved this equation, remember I'm going to use the quadratic formula, -b plus or minus the square root of b squared minus 4ac all over 2a. But we already know that b squared minus 4ac is the number 109. So I can just plug in negative 7 plus or minus the square root of 109 all over 2 times 3. Now this simplifies a little bit to be negative 7 plus or minus the square root of 109 over 6. So if I wanted to solve this, having computed the discriminant already makes the whole process a little faster. If you think that this process might help you remember how to use the quadratic formula, you should feel free to use it. Compute the discriminant first, and then plug your numbers into the quadratic formula after that. And now, of course, I have a couple problems for you to try. You're going to use the discriminant to find out how many and what type of solutions each of these equations have. Now remember, it's only asking you to figure out how many and what type. You don't actually need to solve these equations. So go ahead and pause the video and give that a try. And we're back. So I'm trying to use the discriminant to find out how many and what type of solutions each equation has. My first equation is 4x squared plus 12x equals negative 9. Before I can use the discriminant, I need to get this into standard form. So I start by adding 9 to each side, so that I have 4x squared plus 12x plus 9 equals 0. Now I can figure out that my a is 4, b is 12, and c is 9. Now I plug this all into the formula for the discriminant, which is b squared minus 4ac. The 12 goes in for the b, the 4 for the a, and the 9 for the c. Simplify that, and I get a 0 out for the discriminant. That means that I have one real solution. My second equation similarly started off not being in standard form, so I needed to add the 9 to both sides to get 2x squared plus 3x plus 9 equals 0. A is 2, b is 3, c is 9. Plug that into b squared minus 4ac, and I get negative 63. Because the discriminant is negative, that means that I will have two non-real solutions. Before we go, we're going to sneak in two word problems. This one says, a penny is thrown upward with a velocity of 15 feet per second from the top of a 100-foot building. The height of the penny after t seconds is given by this equation, and it wants to know how long will it take for the penny to hit the ground. Notice that what we have here is a formula where I can plug in a number for the time and figure out how high off the ground the penny is. We want to go the other way though. We want to know how long it will take it to hit the ground. When it hits the ground, its height is 0. So we're going to put 0 in for the height. Now I have 0 equals negative 16 t squared plus 15t plus 100. And now I'd like to solve this equation. Now when I see that this is a quadratic equation, my first thought is to try to factor it. Then I see this negative 16 and this 100, and I think, gosh, if I use the a times c method, I'm going to be looking for numbers that multiply to be negative 1600 but add to be 15. That doesn't seem very likely. I think I'm going to try using the quadratic formula instead. This equation is already in standard form, so I can write down that a is negative 16, b is 15, and c is 100. Now I just need to plug those into my quadratic formula. Here's my quadratic formula here. I'm going to plug my numbers in. I have negative 15 plus or minus the square root of 15 squared minus 4 times negative 16 times 100 all over 2 times negative 16. Simplifying the discriminant, the stuff under the square root, I get negative 15 plus or minus the square root of 6,625 all over negative 32. Now, this is a correct answer. Somewhere in this tangle of numbers is how long it will take the penny to hit the ground. But if somebody asked me how long will it take the penny to hit the ground, I'm not going to answer negative 15 plus or minus the square root of 6,625, all divided by negative 32 seconds. Instead, I'm going to give them a nice decimal approximation. So we're going to do that now. Remember that this breaks off into two separate possible answers. I could have negative 15 plus the square root of 6,625 all over negative 32. Or I could have negative 15 minus the square root of 6,625 all over negative 32. Now I'm going to enter this into my calculator as one big expression, and I just want to show you what that's going to look like. I'm going to put parentheses around the top of the fraction and do negative 15 plus the square root of 6,625. I close the parentheses for the square root, and then I close the parentheses for the top of my fraction. Then I put divided by negative 32. And I get negative 2.07. When I do this again with negative 15 minus the square root of stuff, I end up with 3.01. Now the penny can only hit the ground at one time. Which one do you think it is? -2 seconds or +3 seconds? Time only moves forward as far as we've been able to make it go, so our answer is going to be 3 seconds. Answering with a complete sentence, I will say the penny hits the ground after 3 seconds. One more story problem, then I'll let you go. This one says, given the diagram, approximate to the nearest foot how many feet of walking distance a person saves by cutting across the lawn rather than staying on the sidewalk. Looking at the diagram, we already know that cutting across the lawn takes 40 feet. What we need to know is how far do you have to go if you stay on the sidewalk. Staying on the sidewalk is this distance plus this distance, but we don't know what either of those two distances are, just that this one is 10 feet longer than this one. Fortunately, we can use Pythagorean's theorem to figure out what these two distances are. This is a right triangle, so we know that a squared plus b squared equals c squared, where a and b are the two short sides of the triangle, and c is the long side, the hypotenuse. So that means that x squared plus x plus 10 squared equals 40 squared. Notice that what I did there was I took one of the short sides, x, and plugged it in for a. Then I took the other short side, x plus 10, and plugged it in for b. Now I have x plus 10 squared, and then that needs to equal the hypotenuse squared. The hypotenuse was 40. Now, this is a quadratic equation, and we can solve it using any of our methods. I'm going to start by simplifying a little bit. X squared is the same as x squared. However, this x plus 10 squared, I'm going to need to actually FOIL that out. This is x plus 10 multiplied by x plus 10. And then this whole thing equals 40 squared, and 40 squared is 1600. Let's go ahead and continue working on this here. I've got an x squared. When I FOIL this out, I'll get x squared plus 10x plus another 10x plus 100 equals 1600. Now I'll work on combining some like terms. I have 2x squareds on this side, so 2x squared. I have 10x plus 10x, so 20x plus 100 equals 1600. The last thing I need to do is get this thing into standard form. So I'll subtract 1600 from both sides. That gives me 2x squared plus 20x minus 1500 equals 0. At this point, I kind of step back and look at my equation. This doesn't look like something where factoring is going to go very well. I could solve it by completing the square if I wanted to, but since we're in the quadratic formula section, let's go ahead and solve this using the quadratic formula. In this case, a is 2, b is 20, and c is negative 1500. Plug those all into my quadratic formula, and I'll have negative 20 plus or minus the square root of 20 squared minus 4 times 2 times negative 1500 all over 2 times 2. We'll simplify this just a smidge, and I get negative 20 plus or minus the square root of 12400 all over 4. Now when I break this out into the plus version and the minus version and use my calculator to approximate, I get, when I use a plus, I get 22.8. And when I use a minus, I get negative 32.8. Now let's just stop and take a good look at what we've done. We just found that x is 22.8 or negative 32.8. But x is a distance along a sidewalk, so it's got to be the positive one. X is 22.8. Now let's go back to our diagram. X is 22.8, so that means that this side is 22.8 feet long. This side is x plus 10, so 22.8 plus 10, which is going to be 32.8 feet. Finally, let's go back and just remember what this problem was asking for. It wanted to know, approximately to the nearest foot, how many feet of walking distance a person saves by cutting across the lawn rather than staying on the sidewalk. So if they stay on the sidewalk, how far do they have to go? On the sidewalk, they'll have to go the 32.8 feet, and then they'll also have to go the other 22.8 feet, for a total of 55.6 feet, which is about 56 feet. Now if they walked across here, they'd only have to go 40 feet. So the difference, 56 minus 40, is how much they save. So we'll do 56 minus 40 is 16 feet saved by walking across the lawn. And with that 16 feet saved by walking across the lawn, we're wrapped up for section 8.2. So have fun with your homework, and I'll see you in class.